right, so this is our presentation on our distance sensor car. The basis for what we're working on is a car that's going to sense the distance between an object. So basically, it will follow another car at a set distance, or for example, you'll have a suitcase that'll just follow you around instead of, and it won't hit you, it'll just follow at a set distance behind you. Here's where we built this car. Our sensor is in the front. We just had a distance sensor. Our actuator is a pulse width modulator. Our controller is a Arduino board. We powered it with two 9-volt batteries, and we had a single motor underneath that moved the car. Our model is we based off the velocity of the car. What we did was we took the car at various powers, our motor powers, and we fit a curve to how much power we would supply the car versus how much velocity, and then we were able to calculate how the change of distance based off of the velocity of the person in front of us and the velocity of the car. Now this graph shows our motor power. It goes between 0 and 255 as our max power.
And so moving on to our process gain, we did a couple step tests based on that motor power input, and we assumed that our person was walking at a constant speed here, and that's why you see that it's going further away when we have no power to the motor, and then we ramp up, we slowly start to catch up. So in this process gain is our delta slope over our delta U, which is our controller, our power input. And so we take our final slope, or after the step, minus the slope before our step, divided by the change in our power input. And so with that, it came out to about 1/1000th, or negative 1/1000th, because it's a direct acting system. So as we increase our motor input, you can see that our distance decreases, making it a direct acting system. We have some step tests that we performed with the simulation with our car. And right here we have an optimized KC value of negative 1500 meters inverse. And so with that, we had our car go through some step tests to see how quickly it would respond. Just some key equations in that: we have our power, which is our U bias, plus our KC times our error. Error is obviously the set point minus the distance, and our U bias was the motor power needed to match our walking speed. As we decided to tune it, we did some lower values. As you can see there at the negative 500, it never actually reaches the set points before we have our next step. And if we have a really high KC value, this one's 10 times larger than our optimized, you can see in the controller that it's almost boxed. There are no ramps in the controller, and so that would be a very jerky system. So because of that, we decided to stay with an optimized KC value of negative 1500 meters inverse. And in our system, you can see that there are no oscillations. It's got very short rise time. It's got about 2.5 seconds of settling time. And it definitely lessens the distance. I guess if you have a step back in your distance, then it reaches that set point much quicker than the car can catch up. And this is just because the car speeds aren't very high.
So here's our video that we're going to play, showing our car in action.
Alright.
So we used a big flat board for the car to follow because it helps with our distance sensor, since it's using ultrasonic sound waves. This helps give the best feedback. And right now we're walking at a slow pace, which allowed the car to go slow, and then as we speed up, you can see the car is also speeding up to try to catch up with the board. But as you can also tell, our car has a max speed that limits how fast it can go, so sometimes we'll go a little too fast for it to completely catch up. Now it's speeding up again as we increase the distance, and it's slowly closing the distance. And once it reaches a set point, it slows and it stays at that constant speed to keep the set point. When we slow down, the car is also slowing down, as you can tell. You can see it's trying to catch up to the board now.
Here's our disturbance variable.
Here's our disturbance variable, as it kind of affects the speed of the car a little bit when it goes up and down that ramp. And then when we stop, it slows down until it stops right before hitting our board. So in conclusion, Since our system is a direct acting system, the KC is a negative value. So we got our optimized KC value of negative 1500. And for some future improvements, we could make the U-bias a variable and have that change with the speed of the object that it's following or the speed of the person, because that will affect the distance of the car. And then we'd make the KC also variable based on the speed, because that's also going to change depending on how fast the car and the person are going. And we could also include a y-axis into the model, meaning that we could have the car actually turn and follow the object in front of it instead of it just going in a straight line. Some applications that this could be useful for are, as we talked about in the beginning, a car being able to stop in time if another car or an object is in front of the car that stops, in case the driver isn't paying attention, or you could have a suitcase that follows you, or even some future application could be a trailer that isn't hitched to a car follow the car, and being able to keep the same speed as that. So this is our project. Thanks for listening.